So good afternoon, everybody. So today we have the pleasure to have here Professor Pedro Julian that will give a very interesting talk, as we are going to see. And today we are going to have a session chair, Professor Rafael. But before giving the floor to Rafael to introduce the presentation of Pedro, I just would like to say that we have a great pleasure to have Pedro here today. And Pedro have done excellent work as Vice President of Sequencing Systems Society, representing Region 9. So he has done a lot of work when he was in this position with Sequencing Systems Society. And he was the major responsible to motivate me to be his successor at CASS XCOM. So thank you again, Pedro, for this work. And so now I give the floor to Rafael to do the presentation of Pedro. Thank you again for accepting our invitation.
So thank you, Ricardo. So here today I have Pedro Julian from the Universidad Nacional del Sur, Bahía Blanca in Argentina. Pedro is an associate professor in the Department of Electrical Engineering and Computers at UNS, and he's also an independent researcher in the National Research Council of Argentina, the CONICET. He has a long and fruitful career, being awarded several prizes, such as the Bernardo Jose 2009 Prize of the National Academy of Exact Sciences in Argentina. And he served, as Ricardo said, as a Region 9 Vice President and as a member of the Board of Governors of the IEEE CASS. And today he will talk about building brain-inspired chips in the IoT era. So thank you once again, Pedro, and the floor is yours.
Thank you very much, both. It's a pleasure to be able to join and participate today. You know, during these tough times, whatever one can do to stimulate people. I don't know the situation of each one in the respective countries. In my own country, you know, there's not much we can do outside the house. So all these activities are great. And, you know, I feel good that I can, at the very least, entertain you a little bit. So the title is quite fancy. Of course, we have not yet created any brain inspired chip, but we are moving towards it. And the idea was to provide an introduction to Internet of Things and the challenges that it poses, and then show a little bit some of the things that people, including my group, are doing in research to try to put some processing, particularly in the vision area, to make devices that can perform with the restrictions that we will see that arises in IoT. So to give you a brief description of the scenario, the volumes that are predicted for these devices are on the order of cubic millimeters. And the scale is really quite amazing. It's expected to reach the 1,000 of devices per person. And this is estimated out of the following reasoning. If we can spend $1,000 in a mobile phone that most of you may have, then why wouldn't you have an equal amount of money in $1 cheap devices that you can have not only on you, on wearables, but also on the house, on your vehicle, associated with you. So that's the horizon. That's the scale where this technology is aiming at. And of course, there are many challenges ranging from energy efficiency to useful life, cost, security, interoperability. I mean, there's a lot of things that you need to consider in order for this technology to succeed. In the figure, you can see the Internet of Things and the different layers. So you have a cloud level where you have devices in the order of 100 million of devices worldwide. Pretty big things on the order of meters. Cost expensive, between 1,000 and 10,000 bucks each. Very power hungry, kilowatts at the very least. A lot of computation capabilities, between 100 and 1,000 gigaops per second. They can communicate with no problem, with very low restrictions. And it's already well deployed and very mature. Now you go one level below that and you have gateways and concentrators, where now you have in the order of 10 billion of these devices. They're much smaller. You know, a typical gateway that you have at your house would be, you know, like this size. They're cheaper. You know, it's in the tens of dollars. The power consumption is in the order of 1 to 10 watts. The processing capabilities are much more reduced. They are in the order of 100 to 1,000 megaflops. They're also well deployed and keeps expanding. And then we get to the level where we're interested in the Internet of Things nodes. Now the scale here is predicted to be in the trillions. The size is expected to be between 1 to 10 millimeters. And the price for that scale has to be no more than $1. And what's even more challenging is the power. They will be able to work with a 10 of a microwatt at the very least. And of course, you're not going to get a lot of processing capabilities with that. And you won't be able to communicate much either, because it's very expensive to send information through the air. On this one, we are still far from the target. So it means that there's an opportunity there for us. And one of the main points here is the intelligence that we put at the node. Why? Because there's a massive amount of data that is being collected by these nodes. It's a phenomenon called the data flood. Lots and lots of information, but really quite little useful knowledge. And it will keep growing, you know. And that communication will take huge amounts of information. So the challenge there is to go from the raw data at the very bottom of this pyramid and start to put more intelligence on the chip, to the point where you can send the result of detection or classification, instead of sending raw data for the video that you could be capturing with a camera. You could send something like there's a car on the street. This is the tag license, and that's it. That's a lot less information. There's a lot of less bandwidth, a lot less energy you are consuming. But of course, you have to do that on the chip, and the chip is very small and doesn't have a lot of energy. Then you have to start to think, okay, how are we going to power these devices, and how much can I do? So over here you have a chart where you can see that on the x-axis you have how much power you you can dissipate. So let's say we are in the order of the microwatt. So if you are using a smartwatch battery, you know, you can sustain several years, which is probably what you can do with your with the old watches. Or if you have a button cell battery in the order of a year. But if you have to go, if you start to go really small with, like, for example, thin film batteries or technology like that, then you can just do 1 hour. So it really pushes you in two directions here. So the source of energy will certainly go this way, down, and you will want to move to the left to consume less power to sustain a longer lifetime. And for all of us who do low power electronics, this is key. Now, where are we with this technology? You know, this is a curve that tells you how mature a product or a technology is. So, for example, if you take a look at the right on the graph, you will see the smartphone market. You know, that's extremely mature. So it's, everyone has one. And then you have, if you move to the left, you will see that there are certain points depending on when people adopt a given technology. So IoT is at the beginning. Only the innovators are using this technology right now. Then, you know, you will go to the early adopters, you will go to the early majority, and that will give you to the 50% of the curve. And then you will continue your maturity until the point where it gets like as popular as every smartphone here. So we are at the beginning now. So that's good, because again, it tells us there's opportunities here for us to do things. And also another relevant question is, where are we going to see Internet of Things applications? And, you know, I started to read when I had to give a talk about this, and it really kind of surprised me. When you think about it, it doesn't, but at the beginning it does surprise you. For example, the first technological node is being now Industry 4.0. Why? Because the cost per node is not important. If you have a factory where you manufacture cars, or you are in the oil industry where things are very expensive, you don't care what the price of a node that will measure a variable of something will be. So you pay for it. And really, if the system is closed, in the sense that it cannot operate with standard systems, it's fine too, because you can do a proprietary communication link just to assist that device. Now, that's not scalable. I mean, if I want to have something smart and wearable, I want it to work, whether I have an Android phone or an Apple phone or whatever. I want it to talk to the fridge or to the kitchen or to the TV without having to pay attention to what system the TV or the refrigerator has. So then a second layer would be homes. And the cost is not that low yet. You can see gadgets for homes. I'm sure you do have ones. I do have some. They're not at the $1 level yet. But that's the next step. And then you will have cities and then the followers that certainly at this point they will benefit from the experience and infrastructure of the previous scenarios, and they will develop the characteristics that they need to scale. Into the vision problem, smart cars. So these are all the sensors that you have in a smart car. So you have ultrasonic because you need to know when you're parking if you're going to hit something. You also have night vision cameras, visible cameras to see, people, to record events, to assess distance and direction. You also have 3D cameras to detect, gestures, like do things. You want to have LiDAR, so you can scan the surroundings. A LiDAR, for those who don't know, it's a laser where you scan and you measure the time of the reflection, and then you can estimate the distance, so you can have a 3D map of every object around you. And then you can have radar, millimeter wave radar, to, in the close range, see if there's something that you might hit. So that's a lot of technology. Those sensors, especially the ones, the cameras, they produce a lot of information. So how do you do if you want to process video like that, not only from one camera? Well, this is the standard solution. You take an NVIDIA board as big as you can. So in this system, for example, you have a PX2 computer with 2 GPUs, Tegra Parker, and 4 CPUs, Denver, with 8 ARM 857. And that can give you up to 16 teraflops. And it will be like 250 watts. So if you need this for one camera, okay? So probably you will need one dedicated battery pack just for this. And if you're planning to put 2 or more, I don't think you will be able to drive more than 5 or 10 minutes, and then you will have the choice of just shutting down the camera or continue driving, because power won't be enough for both. So the question is this the smartest thing to do? And let me show you something here, and I will have to show a video now. So let me switch to this video. It's what I'm about to show you. Let me go back here. It's this chip that you see on the low left. That's called the Tianjik bike controller. Okay, it has two neural network controllers, and it's mounted on a bicycle, on a motorcycle, and it has one input which is from a microphone and another input which is from a camera. So, and it controls the speed of the motor, and it also controls the handle of the bicycle. So basically, with these 2 neural networks, you have a full autonomous system that can listen to an operator and act accordingly. Let me show you the video here so you can see it in action. I don't know if you do have sound, but now he's instructing the bicycle to go left. Now straight. Speed up. It's running, it's avoiding obstacles, and you can see on the upper right, he's following the person. So he's able to detect that there's a person there, and he's able to track it. Okay, that's it. And you might be wondering, how much power does this take, right? Well, this takes under 1 watt. It's a 28 nanometer, 40 millimeter square chip and it can deploy 1,278 gigaops per watt. And this is a brain-inspired approach. So it's something that happens when you see and think about nature and how things are done by, for example, the brain. And you will agree with me that I don't know how many megaflops I have in my brain. It takes me a lot of work to multiply big numbers. But when I see something very quickly, and the same is true for any of us, we can detect things. You know, we can detect an old friend from secondary school, even if it's been 20 years and they grew beards and they don't have any more hair, we can still tell that's my friend. So, you know, it's worth to take a look at how the brain operates and try to do something similar. So basically, if, you know, everything related to vision in the brain happens in the back, in the visual cortex. It's one of the most evolved areas that we have. Vision is really key for mammals. And if you take a look at the structure, at the hardware, it has in the order of 100 giga neurons, so 100 times 10 to the 9 neurons, which is, it's pretty large. We are not there yet with the number of transistors we can pack in a chip, but we're close. You know, there are chips with 10, there are 20 times 10 to the 9 transistors. Of course, a transistor is not completely equivalent to a neuron. A neuron is a bit more complex, but we are in the order. Now, when you take a look at the connections between the neurons, that's completely out of the game. That's 10 to the 15 connections. If you take a look at the wiring in a microprocessor, we are completely out of the equation. And this is obviously because we have 3D infrastructure in the brain. Now, when you take a look at the frequency, it's 10 hertz. Not bad, huh? I mean, extremely slow, especially compared with several gigahertz of clock frequency that you can see in processors nowadays. What is the power? The power is 20 watts to power the entire brain. That's amazing. It's an efficiency of 16 milliwatts per cubic centimeter. That's extraordinary. So what is the secret there? Well, the secret is that you just do local communication. You don't send signals far away. Can you hear me?
Yes, we can hear you back now. Your microphone was off for a while, I guess.
Okay. Glad to be back. And then the fourth thing is a balance between the complexity of what you can do and the area of or volume of the cell. There's something there that you need to consider. So in a biological neuron, you know, you have your axon where you send the stimulus, and then you have your nucleus and your cell body, and the dendrites where you get your inputs. So how do we start this endeavor? By making a model and try to abstract what the neuron does to see if we can do something similar. So at the very basic level, what you can observe is that the neurons, they send spikes through the axon, and a target neuron collects those spikes through the dendrites and eventually, after some time, it produces some spikes itself. That's the observed behavior. And how we can model that? Well, we can do several models. So one of them, it's what is called an integrate and fire neuron, where you have a capacitor. And when you exceed a given threshold, you produce a charge that goes to another unit, to another neuron. So basically, you get the input is charge that you get from neighbor neurons, and you integrate that in the capacitor, so the voltage goes up, and you reach a threshold, and you send this output spike, and you reset with that little switch, and you start again. You can also assume that you have some leakage, so you have a resistor, so that integration leaks a little bit. So if you don't have activity over time, you will be down. And you can even make it adaptive if you want. And part of the infrastructure that I show you in the Tianjik chip was implemented with this sort of neurons, integrate and fire neurons. Those are called spiking neural networks. Then you have another sort of abstraction, which is more like an algebraic abstraction, where you have a set of inputs, and those could be, for example, the intensity or the count of pulses that a given neuron sends in a given time. So then you represent that with a number, and you assign a weight to a given dendrite, and then you add them up, and you put a threshold, and you produce an output. So, and that's what people use when they propose the neural networks. They use that model, and then first they proposed a single layer of those, and then an output node where you would add up everything. And then people went on to propose several hidden layers where you have these combinations, lots of parameters that you had to adjust. And they got to a given point, you know. Then, like probably around 10 to 12, 15 years ago, they started to propose a slightly different thing, which is convolutional neural networks, where now you have a kernel, and then this kernel looks like in the slide, like a small matrix like this, you know, the small matrix with the 4 and the -4 and the zeros. That would be the kernel. What you have at the bottom, that would be the image. So the convolution acts like putting the kernel on top of the image, doing a point-to-point product, adding everything up. That, in this case, will give you the number -8. And then you slide one to the right, you repeat and get another output value. And then you slide to the right, and you keep going until you cover the entire image. So this is a little bit different than a standard neural network. It takes a lot of computation to do this. This is something that people started to propose, as I said, 10 to 15 years ago. And they proposed several of these layers. So, for example, they proposed, one of the first things they did was to try to identify digits. So they would take a digit, a very low resolution image, like 32 by 32, and they would put a 5 by 5 kernel. And actually, they would propose several of these kernels and produce these output feature maps. So every kernel now produces a different version of the image, which is a filter version of that image. And then you subsample or you do some trick to keep the information low so it doesn't explode. You discard some things, or you average, and then you do another level of convolution. And then finally, you use a standard neural network to do classification. So This is pretty heavy to implement, and it was particularly heavy 20 years ago. So they started to do this when they had the methods and the computation capabilities to execute these networks. You know, it worked wonderfully with at least 2 layers. It worked wonderfully with at least with digits. So then they started to take a look at more complex things. You know, this is now a deep neural network where you start to put several of these convolution filters. Several, I mean 8, 9, 10, 20, and in the middle you put linear layers. And this is the sort of thing that, and you have to train this. And this is the kind of results that you got. So for example, you put an image of a car, and over here you can see what every layer of the neural network interprets, and how it's combined and transformed along the structure. And then when you get to the final layer, which is a fully connected, that's what the FC stands for. The fully connected, it will give you a histogram where, you know, you will have a higher probability that this is a truck, lower probability that this could be a truck, smaller one for an airplane or ship or horse. And of course, you have to train this. And of course, most of the times, the network will perform very good with things that are very similar to the things you trained. This is one of the most famous deep neural networks. It's called Alexnet. It has 5 convolutional kernels, 3 fully connected layers, close to 650,000 neurons, with over 60 million parameters and 630 million connections. And you know, it can tell 1,000 different categories of things. By the time they proposed this, you know, it was quite impressive. And of course, it took a really big infrastructure to do it, and training would last for days. So this is just to give you an idea. I think we're going to skip this, but you know, it's a lot of data that you have to process, and especially when you're doing a convolutional filter, there's a lot of computation that you have to do while you scan your kernel through the image. These are 3D images, by the way. So there's a lot of computations that you have to do. And also there's a lot of parameters. For example, in this, the first layer of Alexnet, you have 34 kilobytes of parameters. You have 154 kilobytes of input data, and you produce 290 kilobytes of data for the next level. Then you have to do what is called pooling, max pooling, where you take a subset and you try to reduce. And you keep going. For example, when you get to the fully connected layer, now you have 37 megabytes of parameters for the linear part of the neural network. 9 kilobytes of input data and 4 kilobytes of output data. So if you're starting to think of a chip, you know, you have to have those parameters on the chip somehow. And every time, you know, one of these networks cannot fit into a single chip. So if you have a core, you will have to be sending these parameters, performing calculations, and sending another set of parameters. And actually, that takes a lot of power. Actually takes more power to transfer parameters and data than to process. So it's very important, the architecture that you conceive and how you handle the information when you're trying to do these things. As I said, you have to train this. and it takes a lot of time and a huge sample data. And the other question is, okay, you know, how many bits do I have to use when I'm computing this? And if you think about it, you know, it's when you talk about microprocessors, you talk about 64 bits, 128 bits, but how many bits do we really use when we see that friend from secondary school and we recognize him? And there's scientists who studied neurons in the brain, and by doing different tests, they come up that actually it's not very high. In this case, for example, they estimated 26 different distinguishable levels in the synaptic strength. That would be equivalent to how many levels you see in the parameter, in that W that you have to use to multiply with input. So that's approximately 4.7 bits for the parameters. So that's another lesson that we can get. You know, if the brain can do it with a lot of neurons, low resolution, low speed, you know, maybe it's a good idea to go that way. So let me show you a little bit of some neural-inspired processors that are around there, and I will show you some that we did in our lab and some results. So in terms of the platform, you know, at a very general level, you can assess a given platform by the adaptivity or the performance or power efficiency, programmability, and scalability. So these are like 5 major indexes that you can use to qualify a given infrastructure. So for example, if you have a general purpose platform, like a CPU, for example, which is down left. So for that, you know, it can scale very nicely. It can adapt perfectly because, you know, you can do whatever you want. It's absolutely programmable. But then it suffers when you consider the power efficiency and the performance. Now, if we want to improve on power efficiency and performance, well, then we can go to a programmable hardware like an FPGA, and it would also have some degree of adaptivity and programmability and scalability, but not as much as the general purpose platform. Now, if you really want to do IoT, then you have to move to the ASIC arena, where you have very high performance and very high power efficiency, but now it's very tough to adapt. It's very tough to scale, and you know you're gonna suffer if you want to make changes after you burn your chip. And this is an example. This is the TPU from Google that actually made him to save just new data centers and the consumption that would have required. It's a historic array, which is composed of 256 by 256 ALUs, and this provides like 30 to 80 higher performance per watt than a CPU or an equivalent GPU. So it's just 8-bit integer arithmetic. It's quite some power. It's 40 watts, at least for the first version, which is this one that I'm showing here. And it does something similar to a neural network. It has a buffer for local activations, and then a multiply accumulate bank. Basically, when it comes down to neural networks, it's about multiply and accumulate. And so more recently, you have the Google Edge, and on that one, you have up to 4 teraops with half a watt. Again, 8-bit arithmetic. You don't need more than that. And this is something that you can buy for a few bucks. And this is good because now you don't need to build a neural network by yourself. It's something that you can go and buy it. There are a lot of predefined structures. You can train your own, and you can plug it into your system, and you add intelligence there. So this is quite exciting. If you didn't know about this, you can search and buy some of the kits these guys offer and play with it. It's very exciting. We have a couple in the lab. Then you have other beasts like the IBM True North. This guy has 64 by 64 cores with 256 integrate and fire neurons with 256 axons each. Total 1 million neurons and 256 million synapses. Actually, there's no really 1 million neurons. I mean, the unit that you use to compute is the same, but then you have a big RAM where you have the state of every neuron. So whenever you want to execute a neuron, you read the state of the neuron, you do your computation with the multiply accumulate, you produce the result, and you send it back to the memory. So that's the way you do it, to have an equivalent number of 1 million neurons. Speed, they can do approximately 1,000 spikes per second. 8-bit inputs and 9-bit sign parameters. So again, it's in the direction that we want. It's a 4 centimeter square chip in 28 nanometers, and it's in the 58 giga synapse operations per second. Synapse operation is the operation that one of the synapses of these chips can do. And it can reach 400 gigasynapse operations per second per watt of power. Total consumption 70 milliwatts. Now we're talking. This is I mean, for the amount of computation, it's low power. And of course, they were able to put together a large array of these things and do, you know, a lot of proof of concepts with detection of events and in real-time video and things like that. You know, then if you scan the literature, you will see different systems where, you know, they optimize more and more, especially to implement these deep and convolutional neural networks. And again, it's going along the lines that we described. So it's low precision. This chip over here from 2015, 200 milliwatts, 15 million transistors. It has, if you take a look, it has 4 deep net learning cores. Then you have this other one, again, in the order of the tens of gigaops or giga multiply and accumulate per second per watt. A lot of array elements that can process in parallel. And there's, you know, this is several of the things that you can find on the literature. I just put them all of them here to have a reference in case you're interested. This is the Tianjik. This is the controller for the bike that I showed you previously. And this is very interesting because it has 2 different sets of neurons. It has spiking neural networks, and it also has artificial neural networks. It's a 156 core array, and as I said, it's 0.95 watts. By the way, it's one of the first papers I've seen from China in Nature. So a little bit, we don't have much time here, so I will tell you a little bit of the approach that we have investigated in the last decade or so, again, we follow this philosophy where we want to do parallel computation. The cell, we want to implement a cell that only computes with neighbors. We want to have some programmability, but at the same time, we want to do this in silicon. So we don't want it to be very big. And the basic thing that we do at the cell is interpolation. So if you take a look at all the previous chips, it was all about multiply and accumulate, multiply, accumulate. So what we propose is to do a very special interpolation, which is illustrated in this graph. So usually when you have to do a linear operation, you do a plus bx. So you take x, you multiply by b with a multiplier, and then you add a. So we thought about it in a different way. We said, okay, a plus bx is something like what you see over there. So basically what we can do is, instead of doing that product, we are going to have pre-computed the values at the edges, which in this case would be f at x0 and at x1. And when we get an x, we are going to interpolate. You know, if we can tell how far we are from the sides, then we extrapolate that on the top, and we can get the result without doing an actual product. And that's something that you know, in 1D it seems obvious, but you can also do in 2D and actually in n dimensions, as long as you take n plus 1 point. So in 1 dimension, you need 2 points. In R2, you need 3 points for a plane to pass through them. And in general, in Rn, you need n plus 1 points. And it turns out that there's a very interesting architecture that you can use to do that interpolation in time. And that's, the principle is very, very simple. I'm going to explain it here. I'm not going to justify. So if you want to understand why it works, you have to go and read a couple papers. But the idea here is to show you the architecture. So basically, you have a lot of comparators where you have your input. Let's say it's an 8-bit input. So you compare that and you produce this 1-bit time-encoded outputs, okay? Now, you go down and you see the first output that goes down, and that period you're going to call mu1. Then you're going to wait for the next signal to change, and that period you're going to call mu2. And so you go on and on. Remember, these are just 1-bit signals. So far you just used a comparator. And now, whenever you have a set of outputs like that, you go and find in memory one parameter with that digital output, which in this case would be 1, 2, 3, 4, 5 signals. With those 5 signals, you go into a memory and you retrieve a parameter like C1 here. And that parameter you add during that mu1 time. And then you go to the next one, you have another parameter, now it's C2, and you accumulate that during mu2. Is going to after 256 steps, you have a result. That result is equivalent to a multiply and accumulate. And you know, it's a very simple architecture. It doesn't have any products. So on top you have the standard way to do it. So you multiply 2 things and you accumulate in a register. And below you have our architecture. And it has a number of advantages. One of them is that as you're dealing with the values of the function directly and interpolating them, you have less error propagation on those. So whatever you can do in a standard multiply and accumulate, for example, with 8 bits, you can do using this approach with 5. So it's n plus 1, n divided by 2 plus 1. So if you do a standard computation with 20, then using this method, 11 bits would be enough. Of course, we are not thinking in using 10 bits, but we are closer to using 8 or 5 or 4, or as low as the application allows. So basically, if you then compute how much energy you need and how much area, it turns out that whenever you have a few inputs, then this architecture is very small. It takes a little bit more energy than a standard multiply accumulate. Whereas if you have a large number of inputs, you consume less energy, but your implementation is a little bit bigger than a standard multiply accumulate. So we've done a number of chips with this architecture. This is interesting because in neural networks, you really need to handle large number of inputs. It's not unusual to have one layer that takes like 1,000 inputs or even more. So it's very interesting. Now, our first chips, they just had, 1 pixel and 8 neighboring pixels. So at most, it had 9 different inputs. So that was very low. But you can tell this is a system we built on the 90 nanometer technology, and we can get up to 100 gigaops per second with 129 milliwatts, and that's something that in different generations we were able to reduce. This is a system in 55 nanometers where we follow a different approach, something more similar to the True North approach, where we have 2 big caches of memory and the information of the neurons were there, and the computation blocks were on the side of the chip in a column. So every time you wanted to compute a neuron, you will go bring the information from the cache, compute, and send it back. So with this one, we reached close to 7 teraops per watt with the power in the order of the microwatts, with a dynamic power of 3.2 microwatts. A lot of leakage, basically, because we used the wrong set of libraries for the memory. So we ended up with 10 times more leakage than the dynamic power itself. But if you take a look at this, you're in the order of the teraops per watt. And you're doing that with microwatts of power. And this is sort of thing that you can do with a chip like that. Like this is, for example, what you do when you have a color image and you don't have the pixels in between and you have to interpolate when you have an RGB image. And basically with this is a project that we did in collaboration with people in Johns Hopkins, where we had 4 different big chips. One of them had this that I show you. And then we had an FPGA, and we had big memory with up to 16 gigabytes. And all this was interconnected through an interposer. And the idea was to provide a platform for visual applications in IoT. So basically, you have 3 different cores, and they were able to handle different tasks. So the one we designed was that one for visual images. You also had the ability to store a large number of things with 16 gigabytes of memory. And the FPGA was just there for controlling and sequencing operations. This is a picture of the array, pretty big chip. And I'm running out of time, so I'm just going to show you one last slide where you can see on the left axis the efficiency measured in giga operations per second per watt. So that's how much operations you can do per watt of energy. So it's not how much processing you can do, but how much per watt. So it measures how efficient you are in handling or turning the power into processing. On the x-axis, you have megaops per square of silicon, and I mean square is lambda square, so it's somehow normalized to the process. So we don't count nanometers, we count lambdas. For those that know, that's lambda, let's put it simply, it's how small you can do a feature in a given technology. So let's say lambda in a 10 nanometer process would be 10 nanometers, or 10 nanometer divided by 2. In 100 nanometer, it would be 50. So it scales with the technology. So not just by using a more advanced process, you're going to grow on this line. You really need to be doing something smart at the digital level, because you will be dividing by lambda. So this, all the processes that I show you and some more, they are all over the place. So if you take a look at the ones that are up on the right, those more for 1 SIM and more for 8 SIM, those are the chips that we produced. So we are where we want to be. It's efficient, and we are really doing something smart to use our digital infrastructure. Now, the size of the circle, that's how much process you have, net processing capabilities, okay? So there you can see, for example, the big circle is the Google TPU, very big one. And then if you go down, you will see the NVIDIA, the K80. That's pretty big too, but it's intermediate in area efficiency, and it's very low in energy efficiency. And if you take a look at the Tianjik it's in the more or less in the middle. I don't know if you can see the mouse here. The Tianjik, it's over here, and this one SCGVP, that's one of ours. So you know, this is a map showing you the trends and where we think we have to go. So, you know, I think I'm out of time. So I just wanted to conclude by saying that we are convinced that in order to provide application in this arena, we really have to learn from and use the principles of biology. Try to mimic whatever our brain does. Mainly because for many of the things, especially in vision, we are trying to mimic what we want, what we do, what we people do. We want to see people crossing the streets. We want to avoid dangers. We want to avoid animals if we're driving and things like that. And in particular, you know, I didn't have much time to explain our architecture, but that's something that we keep working because, you know, so far it shows that we can do something smarter than just conventional digital circuitry. So with that, I will finish this talk. It's almost an hour, Ricardo.
Thank you, Pedro. Open my camera first. So we got a question on YouTube from João Carlos Bittencourt, who said, besides Asics, is it better to design intelligent applications targeting IoT devices using low-cost FPGAs or board computers such as Raspberry Pi, BeagleBoard, or MCU, taking the advantage of Google Mini TPUs?
Well, I guess you can answer that from different levels, and let me go back to one of the first slides that I had. So it really depends on that. The answer to that question doesn't depend on platform really, but on the application segment. So if you tell me that, here we go. Oops. If you tell me that you are in industry, at this moment, right now, at present, you can do that much of importance. Size won't be that much of importance. Power won't be that much of importance because you can plug it in. So if you have to deploy a solution based on industry 4.0, you can do with a Raspberry Pi, you can do with one of the Google TPU chips. Now, if you're starting to move to other applications, then if you want to wear something here, you won't be able to put a Raspberry Pi here, and you can put a Google TPU chip here because it's very small, but you will have to supply some power. So in that case, you will have to move towards an ASIC, and you will have to move towards an ASIC that is even more energy efficient than a Google TPU. So I would say, to put it in simple terms, it depends what your target is, where your segment in the solution is.
Okay, Fabrizio Alcalde asked the following: how do you test these architectures before implementing them in ASICs? What are the debugging capabilities?
Okay, so PhD students, that would be the most honest question. Actually, going serious, most of these chips, the ones that we produce, are entirely digital. So in our case, we designed these mostly with Synopsys and also with Cadence, some others with Cadence. So in that case, if you follow the complete flow, then you get first silicon success. At the very least, that was our experience with the chips I showed you. When we used the complete flow, we didn't have any issues at all. The chip, you have to simulate, and then you have to verify. And after you do that, you can be almost 100% confident that the chip will do what you simulated.
Okay, in a more philosophical, let's say, space, when you design brain-inspired computers, they are very smart because they can capture patterns that we don't usually are able to, think of the structure, but our brains are generally not so reliable. So what do you think about that? Do you think that if you're going for brain-inspired computing, we will carry this characteristic of unreliability that's inherent to actual bio brains out there?
Let me see if I get your question. You're saying that the brains are not reliable enough?
Enough is a good term, but they are not exactly reliable, let's say. They don't perform exact computations.
No, that's true. And actually, if particularly when you look at perception, the brain actually tricks you a lot. I don't know if you've seen what you get. You get the feeling that something is happening, and there's actually, or you see movement, and there's nothing moving over there. So, you know, in this, even when the title of the talk was very fancy, you know, brain-inspired networks, chips. The point really is, what is the problem you're trying to solve? So in our particular case, what we want to do mainly is to detect things for autonomous vehicles. That's what we want. So it's a very particular task, and we are laser oriented to that end. So in that case, of course, it would be very reliable. The infrastructure is reliable. The results, well, that's kind of questionable, you know. There's a lot of cases and examples where, especially if you rely on these networks, you know, a network is pretty good where when you put inside, it's quite similar to the material you use for training. If what you use is something that you haven't trained, the network, you know, can produce some really catastrophic results. So, you know, it's a mix. I think we're still several decades away from doing something that can be as general as a brain. But for application, you know, I would bet my money on that.
Okay. What about emerging memory technologies such as magnetic or magnetoresistive memories, phase change memories? Because most of the chips you presented here as example, they use standard CMOS as far as I could see. What do you think about that?
Yeah. You know, just by natural instinct, you know, or at least I position myself on the side of mature technologies where you can deploy solutions that can be produced and mass sale on the billion scales. There's a lot of very fancy and promising things, but you know, I think that up to the point where they can be integrated with CMOS, you know, it would be more of a academic thing that you will see on the papers and not a real thing that can be deployed in millions reliably.
Okay. Ricardo also asked, could you comment a bit about digital neurons versus analog ones?
Yeah, well, it's scale. The thing is, you have to, if you're using analog neuron, you will have to, you know, use big transistors, and if you go digital, you know, you can do really, really massive things. You know, even though you could say that the system, when it's based on neurons, it has to be reliable on itself, because you don't trust, you don't rely on the particular characteristics of a given neuron. So your task should be able to perform anyway, even though you have the variability that you have in analog circuitry. But still, when you have to go big, and there's a couple of papers that actually tell you that in terms of energy, digital scales with the log, and analog does not. So it turns out to be much more efficient on the digital domain than on the analog domain.
And what about floating point neurons versus fixed point neurons?
Well, everything that we do, it's not only fixed point, but low resolution fixed point. So that's one of the first things we do when, you know, we want to test a given neural network with our infrastructure. we get, a nominal result from you train your network with MATLAB, and over there you have floating point double precision, and then you start to degrade it, and actually some of the networks they still run with a couple bits. When you degrade those parameters and the operation to a couple bits, they still work. It's quite remarkable. So it's actually a waste to use more than 8 bits. Should be already a waste. And there's quite few papers in the literature that analyze this, and some pay particular attention to how you train these parameters. So there are actually some of these deep neural networks that work with just binary parameters, 0 and 1. So it's, as low as it gets. And they do a lot of tricks where they keep a copy of the parameter in high resolution, but then when they compute with a binary parameter. So they get to keep the gradient alive and working in the back propagation flow. But in the end, the implementation that they get uses an extremely low resolution parameter. So that's where I think that this goes, because if you have to put an Alexnet into something like this, it has to be really small. You cannot afford. I mean, even with 8 bits, it's quite expensive. You have a lot. I've shown you some of the numbers. You have to do just one layer. You need 50 megabytes of data that you have to transfer to do the final computation. So it's a lot of traffic. That's something you have to reduce. And the fact that the neurons in the brain, it just use 4 or 5 bits. That also gives you a hint. There's not much you need. It's not about precision. It's about the number of things that you have in parallel calculating.
Okay. I have a final question in terms of solving problems with neural networks. It seems to me that when we solve problems using neural networks, we no longer dissect the problem we are solving. We are no longer in control of the nature of the problem we are trying to solve. Do you agree with that?
Absolutely.
And do you think that, in the future, we will be solving many problems that we don't know actually the solution for them, and we don't understand the nature of them?
Yeah, that's true. But if that's what happens with our brain, there's something, there are things like I said, telling a friend from someone we don't know, being able to tell the difference with a person that we haven't seen in 20, 30 years. That's, I don't know how the hell we do it. But there's something even more basic. If you ask me, what is the operation? What is that the brain does for consciousness? It's very hard to define consciousness by itself without using the word consciousness. And that's something that is done by the neurons or the pieces that are inside the neurons. So there's a lot that we can learn from what is going on down there. I know what you mean with your question, because I myself, I come from a control system background originally, so I really like to know what's going on. I don't feel comfortable with a neural network that I just trained, and that it does some trick and it says this. But from the point of view of energy and computation density, the structure makes a lot of sense. And that's something worth exploring. At some point, we'll probably be mature enough to realize exactly what's going on inside a network like that. It's very hard to tell though, because when you get into you do a couple convolution and you get 4,000 different outputs, and then you spread that out to 64 different neurons, you cannot even visualize what that is. I mean, it's there are a few papers that try to make sense out of it, but it's really tough. Now, there are other structures that are much more structured, sorry for the redundancy, where you really know what you're doing. For example, over here you have a family which is called deep morphological neurons. And in the morphological neurons, the nonlinear operations are things that you and everyone understands, like edge detection, noise removal. It's basically morphological operations. And those are the core of the nonlinear thing. So you put a range of that, and then you have another part that makes combinations. And for example, for the digits, it tells you which digit you're using, the one of the applications that I showed at the very beginning. And that's something that you can make sense, because you have a digit, you just get the edges, you don't need the whole thing. You just need the edges to tell the number, and then you combine morphology and you can see different features for different digits. Of course, at some point you have to train something, but now you have a part that you really understand what it does, and then there's some other part that has to be trained. But it's a more structured way to just put parameters and train them for weeks and do this works. So that's very interesting. But again, from my viewpoint, what I'm interested is whether it's a deep neural network, whether it's a convolution, or whether it's a morphology. At the root of that is the processing that we have to do, and in the end, it's always going to be multiply, accumulate. So the way we can do that, if we can do that efficiently, then we can do all these other things. And I would say that I'm much more interested on that low level than on a higher level training things.
All right. I'm glad I'm not alone in this feeling. But anyways, I would like to thank you very much for your wonderful lecture. I guess it's a great introduction to the field, as well as for us to know new things. And if Ricardo is there, I'll hand to him. Otherwise, thank you once again.
Yes, thank you very much, Pedro, for this excellent talk.